Hello students, welcome to AIMS India online classes. This is a chemistry session. Here we are discussing about the classification of elements, that is the modern periodic table. In the earlier sessions about this chapter, we have learned about how different scientists they have tried to classify the elements on different bases and their limitations we have seen, and even we have seen the modern periodic table and the special characteristics of this modern periodic table we have seen. In this session, we are discussing about the periodic properties of the elements, how the properties of the elements are being trending in the groups and periods of the modern periodic table. We are going to see here. So out of these properties, we are going to see in this session specially, that is ionization energy. Okay, about ionization energy, we are going to see here. What is ionization energy? How does it vary in the groups and periods? Okay, let us see that. Ionization energy of an element is the minimum amount of energy required to remove an electron from the outermost orbit of an isolated neutral gaseous atom to make that element unipositive ion, that is cation. Okay, ionization energy means the minimum amount of energy required to remove an electron from the outermost orbit of an isolated neutral gaseous atom. So by the removal of that electron, that element becomes a unipositive ion. So the amount of energy required to make it unipositive ion, simply to say, is called ionization energy, which is also called ionization potential. That means if certain amount of energy is supplied to an isolated neutral gaseous atom, then it loses an electron from its outermost orbit. So for the removal of this electron or for the loss of this electron, the energy required by that element is called ionization energy or ionization potential. So we defined here this ionization energy is with certain terms here. Let us see those. The minimum amount of energy required. So whatever the energy we supply, in that minimum energy required to remove that electron from this atom is called ionization energy. Whatever the maximum amount of energy we may supply, in that certain amount of energy will be utilized for the removal of this electron. That remaining energy will be converted into kinetic energy of that electron. So certain amount of energy only is utilized for the removal of this electron. That minimum energy is called ionization energy. Okay, one more term here, isolated neutral gaseous atom. So first of all, before the removal of electron, when we supply energy to an atom, it becomes isolated, means it is separated from the remaining all atoms, and it converts into gaseous form first. So after converting into gaseous form and being separated from the remaining all elements, then the energy required by that element for the removal of its outermost electron is called ionization energy. Okay, ionization potential or ionization energy. This we can say. So isolated neutral gaseous atom is taken in the, and for this an amount of energy is supplied. Then it releases one electron and converts into unipositive ion. There the energy required by that element for the removal of this electron is called ionization potential. Okay. Here as we are telling, this is energy. So its units will be electron volts per atom, kilojoules per mole, kilocalories per mole, etc. In general, when you define this as, when you pronounce this as ionization potential, then the units used will be electron volts. But generally, these all will come as units for ionization energy. So the minimum amount of energy required to remove an electron from a gaseous atom is also called as its first ionization potential. Yes, the amount of energy required by an atom to remove its neutral atom uh, from its outermost orbit is also called as first ionization potential. Then the second ionization potential energy is required. Second ionization potential is the energy required to remove an electron from the outermost shell of an uni-positive charged gaseous ion. Yes, so we told here ionization energy means the minimum amount of energy required to remove an electron from the outermost orbit of an isolated neutral gaseous atom. This is also called as first ionization potential. After the removal of this electron, what happens? It converts into uni-positive ion, that is called cation. Now, if we remove second electron, one more electron from this uni-positive ion, then the energy required by that uni-positive ion is called second ionization potential or second ionization energy. So it can be defined as now second ionization energy. It is energy required to remove an electron from the outermost orbit of an uni-positive charged gaseous ion. Okay. Yes, earlier we have seen in the ionization, one electron is lost by X by the gain of certain amount of energy, that is called ionization potential 1. For the same, if you supply certain amount of energy, some more energy, then it loses one more electron and converts X plus to ion. There the energy required by this uni-positive ion to remove second electron is called second ionization energy or second IP. Okay. For example, if you see sodium, if we supply 495.8 kilojoules per mole energy, then sodium loses one electron from its outermost shell and converts into uni-positive ion. So there, this 495.8 kilojoules per mole energy is called as its second ionization potential. Okay. For the same Na plus ion formed here, if some more energy around 4562.4 kilojoules of energy if it is supplied, then it releases one more electron from its outermost shell, that Na plus ion. There that energy required by this Na plus ion for the removal of second electron is called second ionization potential or IP2 value. Okay. Similarly, we can define the third and the fourth ionization energies of an ionization energies or ionization potentials. If the first ionization energy is considered or represented as IP1 and the second is represented as IP2 and so on, then we can say IP1 is always less than IP2. This is always less than IP3, which is less than IP4 and so on. Actually, theoretically, an atom can have as many ionization potentials as there are electrons in it. So, how many electrons are there in an atom in its shells? Those many ionization potentials can be defined. Just it is theoretically, but no element will lose all the electrons. Of course, practically it won't be possible. Okay. For example, first, second, third, and fourth ionization energies of magnesium and aluminium are shown here. Let us see. See, if you see magnesium, for the removal of first electron, it requires around 737.7 kilojoules. And for the removal of second electron, it is increased, you can observe, isn't it? After the removal of second electron, for the removal of third electron, again, more amount of energy required than the second. And it increases to fourth electron again. In this way, ionization potentials gradually increases because the reason is here, if you see in the neutral state, magnesium has 12 electrons and 12 protons because its atomic number is 12. It has 12 protons and 12 electrons. Negative charge and positive charge both are equal. So after the removal of one electron, what is happening? Number of protons is being same, 12, but number of electrons has become 11. Means positive charge is greater than negative charge. Nuclear charge is more. Then for the removal of one more electron, it requires this much amount of energy. More amount of energy is required. So after the removal of second electron, what is happening? It is remained with 12 protons as it is, but the number of electrons became 10 means number of electrons is reduced. Nuclear charge is much more greater. So it holds the remaining electrons very tightly. For that, for the removal of third electron, much more energy is required. In the same way, for the fourth electron removal too. Okay, that is why first ionization energy will be always less than that of second, that is less than that of third, and so on for any element. We can observe for the aluminum also. Here gradually it increased. Okay. Ionization energy of an element depends on. Yes, on which factors ionization energy depends. Let us see here. First among them is nuclear charge. More the nuclear charge, more is the ionization energy. Yes, if greater nuclear charge is present, then the electrons in the shells of that atom will be held by the nucleus tightly. There, the removal of electron from its outermost orbit requires greater amount of energy, and we are calling that energy as ionization energy. That's why you say more is the nuclear charge, then more will be the ionization energy. For example, if we say between sodium and chlorine, chlorine atom has more ionization energy. Why? Because we know sodium and chlorine both belongs to same period, isn't it? Both have same number of shells, and even from left to right, from sodium to chlorine, atomic size decreases. So size is less and nuclear charge is more for chlorine. It has 17 units positive charge, whereas chlorine is having only 11 units positive charge. So nuclear charge is much greater for chlorine. So it will hold these outer electrons very tightly when compared to sodium. So the removal of electron from this chlorine is a little difficult than the case of sodium. So we can conclude here, as nuclear charge increases, ionization energy increases. Okay. Next factor is screening effect or shielding effect. More the shells with the electrons between the nucleus and the valence shell, they act as screens and decrease the nuclear attraction over the valence electrons. This is called screening effect. Suppose this is nucleus and these are the outermost electrons. In between nucleus and these outer electrons, there are more number of shells between them. So these shells and these electrons will screen these outer electrons from nuclear force of attraction. Thus, the nuclear attraction on these outer electrons decreases a little. This decrease in the nuclear force of attraction on outer electrons because of the screening of inner electrons is called screening effect. Okay, more is a screening effect, less will be the ionization energy. What happens if more number of shells are there and they screen or protect these outer electrons from the nuclear force of attraction more? Then what happens? Nuclear force of attraction on these electrons will be less, so they can be removed very easily. Means they require less amount of energy only for the removal. That we can say as less ionization energy only. So, as the screening effect increases, ionization energy decreases. Because as more screening effect is there, nuclear force of attraction on outer electrons decreases. Hence, they can be removed with the supply of minimum or less amount of energy only. Okay. For example, between lithium and cesium, the element is cesium with more inner shells, and hence it will be having more screening effect, hence less ionization energy. If you observe lithium and cesium, both are in the same group, isn't it? Yes, both belong to same group. But if you observe their number of shells, we know lithium, sodium, potassium, rubidium, cesium, and francium. Of course, francium is radioactive element. Now till cesium, let us see. So among these elements, all these belong to same group. But if you observe from lithium to cesium, number of shells increases. If we see for lithium, it has only two shells. Means between the outer electron and nucleus, there is only one shell to protect that, to screen. Whereas if you see sodium, it has three shells totally. Potassium, four shells. Rubidium, five shells. By coming to cesium, totally there will be six shells. Suppose if it is cesium, there will be five shells in between the outer electron and the nucleus. So these inner shells will shield or screen this outer electron which is present in the outermost shell. So because of this shielding of inner electrons, nuclear force of attraction on this electron will be decreased. So when it is ionization, nuclear force of attraction decreased, what happens? The removal of this electron becomes very easy. That means ionization energy decreases. That's why among these first group element lithium and cesium, the element cesium is having more screening effect and has less ionization energy. Okay. Next factor is penetration power of the orbitals. Orbitals belonging to the same main shell have different penetrating power towards the nucleus. So for example, generally in any orbit, the s orbital is having more penetrating power than 4p than p subshell. So p orbitals are having greater penetrating power than d orbitals, and d orbitals are having greater penetrating power than f orbitals. So for example, it is shown here in the fourth shell, these four orbitals are available, isn't it? Existing 4s, 4p, 4d, and 4f orbitals. Out of these, 4s orbitals are having greater penetrating power than the remaining all. This is a decreasing order. So f orbitals are having lower penetrating power among these all. Therefore, it is easier to remove electrons from 4f orbital than from 4s subshell or 4s orbital. So the orbital which is having greater penetrating power, there the electrons will be held by the nucleus strongly. So the removal of those electrons requires great amount of energy, and those orbitals which are having less penetrating power, in those orbitals electrons are held by the nucleus with weak force when compared to the remaining. So from there electrons can be removed very easily. So out of these four orbitals from 4f, electron can be removed easily with the less amount of energy only compared to 4s. Okay, if you see one more example between beryllium and boron. Say for beryllium, electron or valence electron, that means the last electron, is present in s orbital, isn't it here? Whereas for boron, last electron is present in the p orbital. We know s orbital is having more penetrating power than p orbital. So the electrons in s orbitals are held strongly by nucleus. So the removal of this electron is a little difficult than the removal of this electron. That is why boron has less ionization energy than beryllium. This is due to less penetrating power of 2p orbital compared to 2s orbital. Okay, this is one more factor. Next factor is stable electronic configuration. Yes, some elements are having stable outermost electronic configurations like half-filled configuration or completely filled electron configurations. These elements will attain some extra stability, and hence they require more amount of energy than the expected for the release of electrons. Let us see here one example it is mentioned. It is easier to remove an electron from oxygen, which is having configuration 1s2, 2s2, 2p4, than the removal of electron from nitrogen, whose configuration is 1s2, 2s2, 2p3. This is because nitrogen has stable electronic configuration, that is half filled outermost orbital. If we observe this 1s2, 2s2, 2p3. In the p subshell there are 3 electrons. We know how to represent this p subshell with 3 orbitals. Okay, we can consider this as px, py, pz. Okay, in this way these orbitals are represented. Now there are 3 electrons, 1 in each. Now this is called half-filled electronic configuration. The elements with the half-filled or completely filled outermost orbitals will attain some extra stability. So because of this extra stability, the removal of electron becomes a little difficult from this element. That's why nitrogen has greater electron affinity, ionization energy or ionization potential than that of oxygen. So oxygen has no stable configuration. It has four electrons in this p subshell. So one more electron will come here. That is not much stabler. So electron removal becomes easier than when compared to nitrogen. Okay, stable electron configuration also increases ionization energy. One more factor, atomic radius or atomic size, we can say. More the atomic radius, less is ionization energy. Simply we can compare these two. If the atomic radius is greater, the distance from the nucleus to the outermost electron or electron in the outermost orbit will be greater. As distance increasing, force of attraction decreases, hence electron can be removed easily. So inversely proportional these two. As atomic size increases, ionization energy decreases. So in terms of atomic radius, it is expressed here. As atomic radius increases, ionization energy decreases. Okay. Therefore, for one more example they have mentioned here. For example, the ionization energy of fluorine is greater than that of iodine. What relation between these two elements? Fluorine, iodine. We know these two belong to same group. Fluorine, chlorine, bromine, iodine and acetylene. These are halogen group or seventh group elements we have studied, isn't it? So out of these all, fluorine is the first element with the smallest size. Small size means small atomic radius. So from the nucleus to the outermost electron, distance will be less. Hence electrons are held by the nucleus very tightly. Whereas in the case of iodine, if you see, size is much larger when compared to fluorine. So the distance from the nucleus to the outermost electron will be much far. So force of attraction decreases on that. So the removal of electron from this much easier when compared to fluorine. In the similar way, ionization energy of sodium is more than that of cesium. Why? Because this sodium, potassium, rubidium, cesium, these all belong to same group. In that group, from top to bottom, ionization energy decreases because size increasing. From sodium to cesium, size increases. So as size is greater, distance between the nucleus and the outermost electron will be greater, hence force of attraction will be less. If force of attraction is less, removal of electron becomes easy, isn't it? So between these two, sodium and cesium, cesium is having greater size and lower ionization energy. Okay. Next, now let us see here the variation of this ionization potential or ionization energy in the groups and periods, how it trends. First, let us see how it changes in a big group. Ionization energy in a group from top to bottom decreases. Why? Because size increases. This is because as we go from top to bottom, the size of the atoms increases and attractive power of the nucleus on the outermost electron decreases. Therefore, it is easy to remove the electron and hence ionization energy decreases. See, one example is mentioned here. One group is mentioned. First group elements are mentioned here. Lithium, sodium, potassium and rubidium, cesium. If you observe among these elements, lithium, sodium, potassium, rubidium, cesium, they will be in the one group. In the first group they present. What happens from top to bottom? Size of the elements increases from lithium to cesium because a new shell is being added from element to element as we move down. As size increases, distance between the nucleus and outermost electron increases, thereby attraction decreases. If less attraction, that electron can be removed very easily. Means less amount of energy only required. Hence we say ionization energy decreases. See, they have shown one graph here representing the decrease in the ionization energies of the elements. Gradual decrease. Isn't it? So out of these elements, lithium is having greater ionization energy and cesium is having the least. Okay. Now let us see how it varies in a period. In general, the ionization energy increases across a period because as we move from left to right in a period, size of the atoms decreases. Isn't it? We have studied that in a period from left to right, atomic size gradually decreases. As the size decreases, what happens? Nuclear force of attraction on the outer electrons increases and hence requires more energy for the removal of an electron. That is, ionization energy is much more. Okay. Next, the noble gases are usually associated with the highest ionization energy. We are telling from left to right, size decreases, hence ionization energy increases. So the last column elements are the in any period, last element will be a noble gas. For these noble gases, in generally, there exists highest ionization energies in all the periods. This is because not only because of the size, one more factor is affecting here, that is their completely filled outermost shells. Okay, because of stable electron configuration also they have much more greater ionization energies. So as they're having stable configurations, to remove an electron from those elements, to be it should be distribute that stable configuration. So it requires large amount of energy. Okay. On the other hand, the group 1 elements are usually associated with lowest ionization energy. So we are telling from left to right in a period, atomic size decreases, hence ionization energy increases. The extreme right side elements, that is noble gases, they have greater ionization energies in all the periods. On the other hand, if you say the extreme left side element, the starting elements in each period, they are group 1 or alkali metals. They have greater size in all the periods. Hence, they will be having less ionization energies. Okay, they require very less amount of energy for the loss of electron. Right? For example, look at the pattern from lithium to neon and then compare it with the identical pattern from sodium to argon. See, they have given the trending of ionization energy in the periods. See, first period elements hydrogen and helium. Okay, if you see from left hydrogen to helium, it increased. Next, next period elements from lithium to neon. Actually, it gradually increased. Of course, there are some fluctuations. For that also, there are some reasons that we have some discussed here. Stable configurations in this all. Some we are going to discuss later. So, but generally, gradually it increased in a period because size decreasing. And if you see third period elements, among these also, it gradually increased from left to right. Even the fourth period also started increasing. In this way, in general, to say in a period from left to right, ionization energy increases gradually. This is because decrease in the size of the atoms. Okay. So this is a summary of trending of ionization energy in the groups and periods. So in a group from top to bottom it decreases, means the topmost elements are having greater ionization energies. In a period from left to right it increases. So these elements are having greater ionization energy. So left to right it is increasing. So these elements are having the greatest ionization energies. Out of these also from top to bottom ionization energy decreases. So this topmost element is having the highest ionization energy among all. We can say helium is the element with the highest ionization energy in the modern periodic table. One more also we can derive here. From left to right, ionization energy increasing means these elements are having least ionization energy. Out of these also, from top to bottom, ionization energy decreasing. So we can say this last element is having the lowest. That is, sorry, it is francium, but it is radioactive element. So next to that francium, the element is cesium. So cesium is the element with the lowest ionization potential, and helium is the element with the highest ionization potential among all the elements in the modern periodic table. Okay, that's about ionization energy and its trending. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos.